How Newton perceived gravity was enough to allow us to journey from Earth to the Moon. At any given moment, find yourself lost in the ticking rhythm of time, reflecting on whether our understanding of it is just the peak of the vast iceberg on its surface. His revelation isn't merely a theory. A key could unlock pathways to the universe's mysteries, revealing a universe far more intricate and inspiring than we ever imagined. How does Brian Cox's recent theory challenge our traditional grasp of time? And what could it mean for how we perceive reality? Join us on an engaging exploration through the annals of time itself as we delve into Brian Cox's groundbreaking new hypothesis on the nature of time in the expansive cosmos around us. Secrets await discovery, and some of these secrets revolve around perplexing concepts of time and gravity, fundamental elements of our existence. Picture a world where time behaves oddly. It can slow down or speed up, and the force that keeps us anchored to the ground may not be what it seems. This is the realm of Albert Einstein's theory of relativity, where our interpretation of time and gravity takes an unexpected turn. Albert Einstein, a famous figure, gave us a novel way to view the universe through his theory of relativity. His work laid the foundation for understanding how time functions in various contexts, especially when moving at incredibly fast speeds. The journey began in the early 1900s when Einstein proposed two revolutionary theories: the special theory of relativity and the general theory of relativity. The special theory of relativity, released in 1905, transformed our perception of reality. Simply put, it tells us that the laws of physics are the same for all observers who aren't accelerating, regardless of their motion. This theory introduced the possibility of relativistic phenomena, including the famous idea that time can stretch or shrink depending on specific circumstances. One fascinating mental exercise used to illustrate time dilation is the light clock. Imagine being inside a spaceship traveling at near light speed. Inside the spaceship, there's a light beam bouncing between two mirrors in a direction opposite to the ship's movement. According to the laws of physics, the speed of light is constant for all observers, so the light beam must appear to travel along a longer angled path. The time it takes for the light to complete its journey should be identical for both the observer inside the spaceship and the one watching from outside. However, because the light has to travel a longer path for the outside observer, it seems like it takes more time. This apparent difference in time between the two observers is what Einstein called time dilation. Time slows down for the observer in motion relative to the stationary one. In this case, time behaves in an unpredictable way depending on your velocity. The concept of relativistic effects is more than just theoretical. Scientists use massive machines like particle accelerators, such as the Large Hadron Collider, to accelerate particles to incredibly high speeds, close to the speed of light. When objects travel at such high velocities, we must consider time in a special way to make accurate predictions and measurements. Albert Einstein's special theory of relativity, formulated in 1905, altered how we understand the universe, particularly regarding time and motion. This theory challenges our normal thinking. It states that the fundamental laws of physics are the same for all observers, regardless of whether they are in motion. This is quite different from our everyday experience, where we might assume that adding speed to a moving object makes it go faster. However, Einstein's theory asserts that nothing can exceed the speed of light. This is the ultimate speed limit. From this viewpoint, events that seem simultaneous for us may not appear the same for someone traveling at nearly light speed. Another concept stemming from this unique perspective is length contraction, which means that when something is moving, it looks shorter in the direction of motion when observed from a stationary point. Additionally, the famous equation E equals mc superscript 2 reveals how energy and mass can transform into one another. This is crucial for understanding how tiny particles behave when moving rapidly and also for things like the process of nuclear fission. In this framework, special relativity is not just an abstract theory. It's something we apply in everyday technology, like GPS. When GPS satellites transmit signals to your device, they are moving, and because of their movement, time behaves slightly differently for them. If we didn't account for these time dilation effects in GPS calculations, your navigation would be inaccurate. So, special relativity teaches us that time isn't constant everywhere and for everything. It depends on how things are moving. This idea challenges our basic understanding of reality. It's like saying the ordinary laws we use to explain the universe are incomplete. According to the special theory of relativity, time isn't fixed. It's influenced by motion. Key concepts like the speed of light remaining constant and the interrelationship between energy and mass have been proven in a variety of experiments. But there's more. Enter Albert Einstein's general theory of relativity, proposed in 1915. This theory explores the deep connection between gravity and the structure of the universe. It overturned the old notion that gravity is merely a force that pulls things at a distance. Instead, it explains that gravity results from the bending or curving of spacetime by objects. It's like saying gravity isn't a mysterious force. It's simply the way objects naturally move through the universe. According to Brian Cox's interpretation of general relativity, this means thinking of the universe as a four-dimensional entity combining three spatial dimensions and one time dimension. In this framework, large objects like stars, planets, and even us influence the shape of reality around us. This creates gravity. Imagine spacetime as a large, stretchy fabric. When something massive like Earth is placed on it, it creates a depression. If you place something smaller, like a ball, near this depression, it will roll toward it. This is how objects respond to gravity, not due to a mysterious force, but because of the bending of spacetime. General relativity offers a thorough explanation of how things move within our solar system. For example, it accurately predicts how planets orbit the Sun. Earth's elliptical orbit around the Sun can be precisely predicted by the theory. Brian points out that this is a stark contrast to the old idea of gravity just setting things in motion, which struggled to explain planetary movements. The revolutionary insight is that spacetime is curved like a flexible fabric, and this concept aligns with what we observe. An important confirmation of general relativity came during a solar eclipse in 1919. Sir Arthur Eddington led an expedition to observe how light from distant stars bent as it passed near the Sun. According to the theory, the Sun's mass should cause the light to curve slightly. During the eclipse, the observations confirmed Einstein's predictions, providing significant evidence for the theory. Just as motion can alter our experience of time, as per special relativity, gravity also impacts time. In areas with intense gravity, time moves more slowly compared to regions with weaker gravitational pull. So, if you were near a massive object like a black hole, your clock would tick slower than one situated far away from the immense mass. General relativity introduces the concept of black holes, regions where gravity is so strong that nothing, not even light, can escape. The boundary around a black hole is called the event horizon, which marks the point of no return. Once something crosses this boundary, it gets drawn into the black hole with no way to escape. Einstein's general theory of relativity has major implications for the structure of the universe. Initially, Einstein introduced a cosmological constant in his equations because he believed the universe was static. However, when scientists discovered that the universe is expanding, he later called this a great mistake. The concept of an expanding universe, based on general relativity, forms the backbone of the Big Bang theory, which explains the origin of the universe. Another important idea from general relativity is gravitational waves. These are ripples in spacetime created by the motion of extremely massive objects, such as when black holes or neutron stars merge. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves for the first time, offering further proof of Einstein's theory. Over time, scientists have conducted numerous experiments to test general relativity, and it has always stood up to scrutiny, whether through studying planetary motion, observing the bending of light, or detecting gravitational waves. While some may be astounded by the everyday reality of gravity, in the world of physics, it's natural to question and challenge established theories. In the case of gravity, many scientists probe how we think about this essential force. One theory that challenges traditional gravity is called modified Newtonian dynamics, MOND, which suggests that gravity behaves differently at low speeds, particularly within galaxies, without requiring the existence of dark matter. Instead of adding unseen matter, MOND proposes that gravity strengthens at low speeds. The gravity debate also involves the elusive ideas of dark matter and dark energy, which were introduced to explain certain cosmic phenomena. Critics contend that these concepts may not be necessary and that alternative theories could explain what we observe. Some scientists who reject Einstein's theory of gravity explore other potential explanations, such as unknown particles or forces that might adjust or improve our understanding of gravity. It's important to note that in science, new ideas are rigorously tested to see if they hold up. For example, Einstein's idea of time as the fourth dimension, where time travel could be restricted by the speed of light, has been creatively paired with ideas like wormholes and shortcuts in space-time. Stephen Hawking's chronology protection conjecture suggests that traveling back in time is improbable from a physics standpoint. Ongoing experiments and observations aim to determine whether these new theories can account for phenomena such as the force of gravity in a way that aligns with established knowledge. While various theories have been explored, none have convincingly replaced the well-supported principles of gravity. Questioning and testing established ideas is fundamental to the progress of science. These investigations foster deeper insights into the universe. As for gravity, general relativity remains the most significant and well-tested theory to date, explaining various phenomena like the movement of planets and the bending of light around massive objects. General relativity holds strong because of its simplicity and ability to explain numerous observations, such as the way planets orbit the sun. Einstein's special theory of relativity reveals that time behaves differently depending on one's motion. Let's explore how this impacts practical scenarios, especially in the realm of space travel. Space exploration is thrilling but immensely challenging due to the vastness of space. Moreover, according to Einstein's theory, the speed of light is the maximum speed at which anything can travel. This creates a formidable challenge for space travel, especially when trying to reach the nearest stars, given the immense distances involved. To better grasp what happens to time during space travel, we can consider the famous twin paradox. In this thought experiment, one twin stays on Earth while the other embarks on a swift journey to a distant star. When the space-traveling twin returns, they find that far less time has passed for them than for their twin back on Earth. This means they have effectively traveled forward in time. Time plays a critical role in space exploration because over long journeys, time slows down for those traveling at high speeds. If astronauts were to visit nearby stars, where time dilation becomes significantly more noticeable, they could age more slowly than those remaining on Earth. Although this may seem like science fiction, it's a real effect predicted by the theory of relativity. Imagine a mission to a distant star system. Given the vast distances involved, such a journey would take many years. Even at high speeds, astronauts on board the spacecraft would experience time at a slower rate compared to those on Earth. The influence of time dilation affects both living beings and technology. For instance, GPS systems and communication satellites in space need to account for time dilation to function accurately. Space travel also presents a range of challenges, including exposure to cosmic radiation, the mental effects of isolation, and the physical impact of long-term confinement. In our daily lives, we can observe the effects of time dilation in systems like GPS. These systems depend on precise timing from satellites in motion. Since the satellites experience time differently than we do on Earth, failing to account for these differences would result in inaccurate positioning. Finally, let's explore why time seems to flow in one direction. Time controls our existence, moving from the past to the present and into the future. But why is time unidirectional? This is where entropy comes in, an idea that measures how disorder or randomness increases over time. Entropy, linked to the arrow of time, tends to grow, causing time to advance in one direction. The second law of thermodynamics asserts that in any closed system, total entropy will either increase or stay constant. In simpler terms, entropy naturally increases and never spontaneously decreases. This growing disorder helps us understand the one-way flow of time, as we witness in everyday events like ice melting or a stirred cup of coffee becoming chaotic.